Hi, Elliot. Hi, Dave.
Hi.
How are
Hi.
you? How was your Thanksgiving?
Good, solitary. Having two of us.
Yeah, same here, quiet.
Uh, well, I wonder if I scared off everyone under the age of, how old are you, Dave? 55, 60?
I just turned 65 yesterday.
Congratulations.
Welcome to Medicare.
Yeah, I know, right? I don't think I'm supposed to do anything if I don't want to yet, since I still work.
Yeah, as long as you have health insurance through Columbia,
Yeah.
there's no problem. Well, I tried to convince the students that I was going to ease up on them, but maybe they're too far gone.
Well, swimming through choppy waters when you only partially understand is something we have more practice with.
Yeah, right. Yeah, when you're sort of 3/4 lost.
Yeah. I mean, I figure when people translated languages they didn't understand in foreign countries 200 years ago, I mean, they were just like listening and picking up patterns. You know what I mean?
Yeah.
So I am subbing for Danielle at a chairs meeting on Wednesday. I think I can leave the screen on my laptop. It may not look the same. Oh, there we go.
There's Leah.
Hello, I'm here to remind you to record because I have class in 15 minutes.
I'm sorry, what did you say? You want me to record it?
Yeah, I'm here to remind you to record.
Oh, he is recording.
It's
Yeah,
recording.
that's great. That's great.
Well, shall I go ahead?
Sure.
So I want to do two things today. And as I indicated in my message, whenever it was Friday, I'm not going to be by any means covering all the details. But I want to finish in some reasonable amount of time. And as we know, I've sort of gone over the head of much of the audience. So I will ease up a little bit. All right. So the two things I want to do today is, oh dear. Oh, maybe I need to make a new one.
Has the tip unscrewed a little bit?
No.
Oh.
And I had it plugged in.
Try remating it with the app. Yeah, there we go.
Yeah, there we go. All right. Yeah, all right. So the first thing I want to do is complete the argument that the space of descending paths is equivalent to the space of elementary descending paths. Which we've already seen to be then equivalent to the space of descending disks. So we have when I talk about a descending path, there's one critical point, which is in a level that doesn't have any other critical points, and you're moving it down past various critical levels without changing anything else. So that's the space of these descending paths. There's a special class of subspace of them, the elementary descending paths, which come from embeddings of standard neighborhoods around the critical point, and then just some standard deformation in that model. And we've already seen the space of elementary paths is equivalent to the space of descending disks, and now we want to get back from the space of elementary paths to the space of all paths. So that's the first thing I'll do. And the conclusion will be of this is that to understand, classify descending paths, the general descending path up to deformation or homotopy is to understand these descending disks. In Morse, canonical Morse neighborhoods. Okay, so that'll be the first thing I want to do today. And the second is that I want to apply that result in three special cases and completely classify pi naughts of the components of the space of descending disks from a critical point in all three cases. And those cases will be used in when we start manipulating our diagrams. So let me just back up a second and say what we're doing here is we're moving from information that the diagram gives us about the way critical points, the values of critical points move around, to actual results in the space that say when you can make movements that from the perspective of the graphic of the Morse function or the family of Morse functions might be something you want to do to simplify the graphic. This tells you when you can actually do it by paths of functions, the Morse functions or almost Morse functions in the space. So we're adding the extra ingredients that are not captured in the graphic, which is just a two-dimensional picture of the critical points and their height and critical values. We have to get back into the manifold, and that's what studying the space of disks allows us to do. It tells us what paths we can actually, crossing paths at least, we can actually realize, because we figure out what kind of descending disks we can find. Okay, so that's what we're going to do today. So let me recall where we are on the first topic. So we have a setup here. W is our cobordism. F is a Morse function. It has a critical point C naught with critical value alpha naught, which is a simple critical value, meaning no other critical points at this critical value. And then we have the next P critical values. Okay. And we're interested in paths, which I'm going to call CPF. These are paths in the space of functions. I guess I called it F of V, but anyway, space of functions on V cross I. Beginning at F. So it's an interval, a path in the space of functions that cross so that under the path, alpha naught moves so as to cross alpha 1 up to alpha p in succession, and no other, shall we say, activity as far as the critical points are concerned. So that is to say the multiplicities of the alpha I are constant through the path. If there were R critical values at alpha, R1 critical values at alpha 1, they remain moving in tandem, always keeping the same critical value. So alpha 1 is allowed to move, but all the critical points that originally had alpha 1 as value move with it. And no other, so multiplicities are constant and no other crossings and no births or deaths. So this is a family of Morse functions. They're not excellent Morse functions. They can have multiplicities in their critical values. This one only has one critical point. And what happens under this path is that this one critical point, it moves so that its critical value collides with alpha 1, giving a codimension 1 stratum where you have an extra critical point at this value, whatever it is at that point. Then it moves, it crosses, moves below alpha 1 to alpha 2 and so on. So it crosses all p of these next lower critical values and crosses no others. So we're specifying exactly how many critical values, critical levels, this critical value is going to cross. It crosses them, goes across them, doesn't come back, and eventually ends up below alpha p, but higher than the next critical value. So that's the space of paths we're considering. These paths lie in, so let's let FPF be the union of the images of the gamma in CPF. Okay, and so that turns out to be, it's a union of two types of strata. Strata where there's one fewer critical value and one of these critical levels has an extra critical point in it. Those are the codimension 1 strata where these things are colliding. And then the codimension 0 strata here are Morse functions where you have whatever the multiplicities are here are the same, and this singleton here is somewhere in between alpha I and alpha I plus 1. So this space has a stratification, FP0. This is the open set where alpha naught is distinct from alpha 1 up to alpha p, doesn't agree with any of the others, and the codimension 1 stratum where alpha naught agrees with some alpha j 1 less than or equal j less than or equal p. So you have these collisions, these crossings, and those are codimension 1 strata. A function that would define locally the codimension 1 strata would be the critical value of alpha naught minus the critical value of alpha j. It vanishes exactly when you're in this stratum. Okay. Okay, now inside this space, we have the space of, I guess I called it EL, elementary paths that cross these P levels starting at F. These are elementary descending paths. Starting at at F, and they come from Morse neighborhoods, the standard Morse neighborhood of the critical value, critical index R embedded in W, and then a standard path H mu here pushed in. And then you get a collection F mu here. This path is constant outside this neighborhood, and in the neighborhood, it agrees with this H mu, which goes -1 to 1 under some embedding. Okay. So we have standard models and standard paths given by explicit functions in the model, and we're looking at all embeddings of the model into W and push that path forward. And we are requiring, well, it starts at F at value 0. So it gives me a path starting at F, and I'm requiring this path pass these P critical levels. Okay, so that's a subspace, elementary paths PF inside all of these paths. And the theorem, well, at level 0, which is really almost all I need. Occasionally I need something about pi 1, but level 0 says that every component of paths contains an elementary path. I don't know how you want to write this. In other words, this pi naught is trivial. Every component of paths starting at F, crossing these P levels, contains an elementary path. So if there's any path that crosses these levels, then there's an elementary path. But the stronger theorem is that, in fact, the homotopy groups of this space modulo the slightly funny version of the elementary paths based at any elementary path, these homotopy groups are trivial for all star greater than or equal to 1 and all elementary paths. Okay. So this is, remember, the simplicial set made by not considering the singular simplicial set of elementary paths, but only using simplices in elementary paths that lift up to the embeddings of the standard model. And then, I mean, this is really 99% of the time, this is all I'm using. And this is really a statement about the space of elementary paths, because there's 0 simplices of space of elementary paths. It's just the points of elementary paths. So it says every component of this space of paths contains an elementary path. And then the corollary is that pi naught of the space of paths is identified with pi naught of the space of descending disks, which are disks, the image under one of these embeddings of the standard descending disk, past P critical levels, and the neighborhood is associated to F and, if you will, C naught. Good. Because we've already proved that the space of elementary paths is equivalent to the space of, well, in this form, is equivalent to the space of descending disks. That's what I proved over the last couple of weeks. So this is the result. It's going to tell us when there are spaces of descending paths from a critical point crossing some number of levels starting in a function F, you have to find a descending disk. Okay. All right, well, this is what I've got to prove. So the proof goes in proof by induction. The case, so we're going to prove this by induction. We have to do the case P equals 1 directly, and that's a nice argument. I'll show you that. And then we have to do an inductive argument where we cut paths in half and cut paths into shorter ones and just use a standard inductive argument. Okay? Okay, so P equals 1. So I'm going to consider not only CPF, these are the paths across P level starting at F, I'm going to consider a larger space, CP. These are good crossing paths, crossing P levels, that are homotopic through good crossing paths to F. So let me just draw a picture. Well, in the case P equals 1, here's F. If I have a good crossing path, this is a family of Morse functions. This is inside this FPF. I have F and I have one of the codimension 1 strata, FPF1, that F crosses. So this would be a gamma in here. And another element, mu, might go from F1 and cross the same stratum, and there would be a homotopy here of paths that cross this stratum exactly in 1 point. So I will be, this path would be a good crossing path, and what you see here is a homotopy of good crossing paths between it and F. So all these paths CP lie in this space I've called CPF. All of their images are in this same stratified space we've talked about before. So remember, this is a space of Morse functions. It's just, they're not excellent. They're critical values that have multiplicity. Okay. All right. And now, similar to the elementary paths beginning at F inside CPF, I have elementary paths beginning anywhere inside CP, anywhere in F naught in the top strata. Okay. And what I want to show, what I really want to show is that pi naught of CPF elementary paths is 0. Well, I want to consider 2 maps from, so I'm not going to directly consider CPF for a while. I'm going to consider all of CP, this bigger space. And I have 2 maps from F, from CP to this space of Morse functions. I have one which is the initial point, I'll call it I, that just sends a path to gamma of 0, its starting point. The fibers of this map will be the various CPFs as you let F being the image. Okay. There's another map, which I'll call CR for crossing, and it goes to the codimension 1 stratum. And this is the crossing point. The unique point in gamma T intersect FP1, because I'm considering now the case when P equals 1. And so there's only one crossing. So the crossing point is a function from the path space to the codimension 1 stratum. The initial point is a function from the path space to the top stratum. And the proposition is that I and CR are locally trivial vibrations. In fact, locally trivial so that the elementary paths are also locally trivialized by the same isomorphism that I'm going to produce. So there are local trivializations, if you will, of the pair CP elementary paths P over, well, either F naught or F1. So you have a product, locally you have a product of this pair of fibers with an open set in the base, homeomorphically onto the open set in the total space. So both of these, initial point and crossing point, are locally trivial vibrations. This one's a locally trivial vibration over F naught. This one is a locally trivial vibration over F1. Let me suppose this for a second. I'll come back to the proof. Okay. Well, anytime you have a locally trivial vibration, well, okay, let me back up a minute. Let's consider CPY, which is crossing inverse of Y for some point Y in FP1. So let's consider a fiber of the crossing map. Let's call the image point Y, and let's look at all, these are all paths where Y is the point where the path crosses the codimension 1 stratum. Okay. Well, this space is contractible. For the usual reason, if you have any path crossing at Y, you simply shrink that path down arbitrarily close to Y, and then you're looking at paths in a little neighborhood, and the neighborhood is contractible in this direction. So there's nothing interesting about these paths, the usual sort of argument for spaces of paths. And secondly, there exists an elementary path through Y. Okay. So that says pi naught of CPY elementary paths at Y is trivial. This is a contractible space, and this is a non-empty space. So every component of this space has a point of that space in it. Now we have a locally trivial vibration over the base with the fibers that have, the fibers are connected, the big fiber is connected, and the small fiber is non-empty. Okay. So that implies that pi naught of the total space, CP, modulo the elementaries, is also 0. So if you have any point in CP, it lies in one of these fibers. There is a crossing point, and you can deform it in that fiber down into the elementary path space. And therefore, every component of CP has an elementary path. Okay. Now we use the other locally trivial vibration. We have CPX elementary PX. So these are the fiber over the initial point. Okay, so these are the paths that, maybe I should call it F to be consistent with what I did before. These are the paths that start at F, all of them, and elementary paths. Well, these are the fibers of this locally trivial vibration. Okay, so these are the fibers. Pi naught of this space is trivial, therefore pi naught of this space is trivial, of this pair. Because if you have any point in CP, if you have any point, so let me just prove this for you. So I have gamma in CPF, it's a path. I know it's therefore a path in CP. I know that gamma is connected to an elementary path, mu, which may not be in the same fiber, but let's look at the image under the projection, I of gamma and I of mu. The path between these gives us a path in the base between I gamma and I mu. But now the fibers are along this path are all homeomorphic. So there's an elementary path in this fiber, and therefore there's an elementary path in this fiber, just using the local trivialization. So I turn this argument around, if you will. All right, well, this is all based on the proposition that these pairs of fibrations are locally trivial. And the argument is the same in the two cases. I'll give it in the case of the initial point map from CP elementary point P down onto F naught P F. Okay, I'll show this is locally trivial vibration. And what I'm going to use is the fact that look at the component of the identity of the diffeomorphisms of W across the diffeomorphisms of I, orientation reverse, preserving in both cases. This acts on F, PF, preserving the stratification. Clearly, just action of the diffeomorphism group. Doesn't change the fact that you have these Morse functions, just doesn't change the critical value structure, number of critical points, and so on. Okay, I claim there exist local sections for the action of G on FP naught, meaning given F prime in there exists a neighborhood of F prime and a continuous map from U into the group such that sigma of F prime is the identity, and sigma and for all F double prime in U, sigma of F double prime acting on F prime is F double prime. So in other words, I have this neighborhood, I can lift it up into the group G so that the central point goes to the identity And if you act by these group elements, you exactly sweep out the neighborhood. That's what I mean by a section. Okay. Well, this group also acts on the paths with this crossing behavior, a single crossing point, because it acts on this space, this stratified space, preserving the stratification. Okay. So now I can go from the fiber over F prime across this neighborhood into the part of the full space that sits over the neighborhood by sending F1, a function, I'm sorry, gamma 1, gamma, a function in here, beginning at F prime, comma, F double prime, that's a point in U. I just send it to sigma of F double prime, that diffeomorphism acting on gamma. And that will give me a new path. It will begin at F prime because sigma of F double prime acting on F prime is F double prime. And this is a homeomorphism from the fiber over this one point across the open set of the base to the preimage of the open set. And that gives the local trivialization. And since these diffeomorphisms, G preserves the elementary paths, this implies the trivialization carries the elementary paths beginning at F double prime cross U onto the elementary paths beginning at any point in U. So it's a trivialization of the pairs. So that's the argument that the initial point map is a local trivialization. The argument for crossing is identical. Okay. So this proves for P equals 1, CPF and elementary paths PF satisfy pi naught. Every component of a path from F with one crossing can be deformed, keeping F fixed to an elementary path with one crossing. And as I've said before, but I'm not going to emphasize it, if you move over into the simplicial world, you get the higher homotopy groups as well, though I'm not going to make any use of that. Okay, so that's the case P equals 1. Any questions about that? Okay. So now, what about the P greater than or equal to 2? You're going to go by induction. Maybe I'll just give you the basic idea. How am I doing all the time? Yeah. And not think too much more. So we're going to suppose P is greater than or equal to 2, and suppose we know the result for all P prime up to and including P minus 1. So we're interested in studying this space where now P is 2 or more. But by this local vibration argument, it suffices to consider pi naught of CP epsilon P, ELP. In other words, don't pin down the initial point, allow the initial point to be anywhere. And now we want to consider paths here's the first crossing. It's going to take place at lambda 1. So this is in the space. This is a picture of the path in the space FP. So these are the codimension 1 strata. The first 2 crossings are going to happen at a time parameter lambda 1 and lambda 2. And we're going to have a parameter value mu between these two. Okay, and our path starts up here. So I'm going to consider paths. The first crossing at lambda 1, second crossing at lambda 2, those are going to be fixed. And at mu, which is somewhere in between lambda 1 and lambda 2, the path gamma of mu is some fixed f prime in f. Okay. So instead of considering, so I started by needing to consider paths that started at a fixed f, but because of this local vibration argument, I can drop the condition on f and consider all paths, no matter where they start. Now I'm going to pin down the first and second crossings and the value at mu. Well, once again, these same sort of argument shows that this is one fiber of a locally trivial vibration. So once again, it suffices to prove the result for this set of paths. Suffices to show that pi naught of these paths, let's call them CP prime. So lambda 1 and lambda 2 are fixed, mu is fixed, and the value of the path at mu is fixed. We denote that by prime. If we have an elementary path with these conditions, we'll call it prime. Suffices to show that this fiber has the condition we want, that pi naught vanishes. It, of course, will also be true that if you take this simplicial version, the higher homotopy groups vanish as well. Because if you know it for these fibers, then you know it for the total space. If you know it for the total space, you know it for this fiber in a different vibration. Okay. So now we're going to break the space of paths into a space of plus paths and a space of minus paths. So this is simply, you have gamma, this is simply the restriction of gamma to 0 mu, call that gamma plus, and this is the restriction of gamma to mu 1, and call that gamma minus. So you look at this part of the path, you don't know where it starts, but it ends at f prime, that's the gamma plus. And then I have the rest of the path, which goes on down. I haven't drawn it, goes through all the rest of the critical values, and we'll call that gamma minus. And then we have the elementary path version of this. Elementary P plus cross elementary P minus. And these are included. So P plus has one crossing. P minus has P minus 1 crossings. And so you go by induction. Each of these factors is a homotopy equivalence. This is a homotopy equivalence to all the paths, and this is a homotopy. This is in fact a homeomorphism to all the paths. So you just use induction. We need the result for one, and we need the result for p minus one, and this sort of breaking it into two pieces this way. Okay, so that's a sketch of the induction that allows you to show pi naught of CPF elementary paths PF equals 0 for all P greater than or equal to 1, all F of the type we were considering Morse, with so on and so forth, the other conditions we are assuming. All right, and then of course, this becomes isomorphic to the disks that cross P levels starting at F and based at the critical point C naught through the elementary paths. So we'll just write that this way, corollary. Given any crossing path gamma in CPF, so it starts at F and crosses P values. There exists an embedding of the model, the standard path H mu gives me a path F mu 0, 1. This is an elementary path crossing P levels, critical levels. Such that gamma is homotopic rel, the initial point, to F mu. The path constructed this way, and then we associate to that the descending disk phi of the standard descending disk in the model. So that's a descending disk out of the critical point that crosses alpha 1 up to alpha p, crosses these p critical levels. So gamma is homotopy rel the endpoints to this elementary path, which comes from an embedding and therefore has associated to it a descending disk that crosses these levels. If you want to understand the homotopy classes of all paths, you simply, through this mechanism, have to understand the homotopy classes of possible descending disks out of this critical point crossing these p levels. That's what this theorem says. All right, now to the applications. I'm going to give you 3 applications. Oh, I don't think I'll probably won't prove the third one. Well, let me give you the setup for these applications, all of them. We're going to have our specific, our central critical point, the one that we work with, C naught. And it's going to have a descending disk. The first level that we talk about is V naught. The last level will be VQ, because we're going to pass Q critical levels. And this manifold between the two is W0Q. So V naught and VQ are regular levels for the function F. and W is the manifold with boundary in between them. And our assumptions are going to be, I'll draw a picture again, maybe a little bit more schematically, fewer dimensions. Here's C naught, its descending disk down to level V naught. There's a descending manifold for this that goes all the way down to VQ. There are these various critical points in here, and they may be several at each level. They have ascending manifolds. Oops, I don't have much room for that one. And maybe I'll forget this last critical point, since I don't seem to be able to draw it. So the ascending manifolds from the critical points C1 up to C, however many there are in critical points inside W 0Q. We have those ascending disks, and we have this one descending disk. They're all disjoint. These are assumptions. And the descending disk from C naught goes all the way down to VQ, and the ascending disk from the various critical points in W0Q go all the way up to V naught. And there are all these manifolds, the A and the descending disk, the A's and the descending disk D are disjoint. Later, we're going to need notation. This sphere is called X, and Y is the intersection of A with the with V naught. So it's the union of these ascending spheres. Now, of course, we have descending manifolds as well, but I'm not drawing them in this picture. So these are the assumptions. And the question is that we're going to answer, at least in some cases, what is the number of components of the descending disks from C naught for F, from C naught down to level VQ. So what is the space of these descending disks up to deformation? Okay, so 3 cases. Case 1, if the index of the CJ is greater than the index of C naught, which we'll call I, for all 1 less than or equal J less than or equal to N. So if all these points have index larger than this point, then pi naught of the space of disks is connected, and hence there exists up to homotopy a unique descending path for F at C naught down to level V naught. Okay. Because the space of paths is the same as the space of disks, and up to deformation is only one disk. The second application is if the index of CJ equals the index of C naught, which is I, for all. So the next case we want to consider is when these points all have the same index as C naught. Then there exists a bijection from the component space of the disk to hi of W0Q mod VQ. So the homology of this manifold modulo its bottom, which is, after all, just the free abelian group generated by the C1 up to Cn, because each one of those critical points produces a descending disk of dimension I, di1, di2, and these are, of course, generate the relative homology. The W0Q deformation retracts onto VQ union these disks, and therefore these disks are the relative, are a basis for the relative homology. And if you have a homology class in here and you want to know what linear combination of these disks it is, you just intersect that cycle with the ascending manifolds out of the critical points. You get an integer for each critical point. You take that linear combination of the disks. Okay, now to get this bijection is fixed or is determined by a choice of a basic disk D naught and an orientation of D naught. So I already have one. I might as well let that one be the basic one. Okay. And here's how the bijection goes. Any D in this space of disks, oops, in the space of disks, deforms to be equal, to agree with D naught above V naught. Okay, so you may have another descending disk. It may not agree with D up here. It may not agree with D naught at all, but you can deform it uniquely up to homotopy, in fact, so that above V naught, it actually agrees with D naught. Okay, so that much of it's going to be the same. Okay. And now D and D naught, so D and D naught, or let's take D minus D naught. So I have two disks now. Here's D naught, here's another one, D. Might look like that. So I'm imagining D looks like this. Okay. But it has the same, it agrees with D naught up here at the top, this top sphere. And therefore the difference is a cycle a relative cycle in W0Q VQ. Because the bottoms may well be different, but at the top, they agree. So you take their difference, this boundary will cancel out, and you're left with a cycle relative to V naught, to VQ. And of course, it's just the intersection number of this second disk with the ascending manifolds out of the critical points, because the first disk by construction didn't meet the critical points. Didn't meet the ascending disk. So this is just the intersection. So the class of D minus D naught in HI of W0Q VQ is given by the intersection numbers with the ascending manifolds, the A1 up to AN, the ascending manifolds out of these critical points. Okay, as you see here, I have these points of intersection, okay, that would contribute to the actual linear combination. Okay, so that's the bijection. It requires orienting the disk, requires fixing a disk D naught. We've done that. Orienting D naught. Once you orient D naught, that determines an orientation for any a descending disk. So D has its induced orientation, so this thing is in an oriented cycle. You take its relative homology class, and that tells you the number of components. I mean, this should remind you of Smale's handle sliding argument. What we're doing is proving that the descending disks are exactly given by these, that the components of descending disks are actually given by the handle slides, all possible handle slides. In this case, when all the indices are the same. And the third case, which I definitely won't have time to get to, is the case when F restricted to W0Q has exactly two critical points, C1 and C2, and they cancel each other. So they've been created by a birth, actually. Okay, then the space of descending disks is trivial, provided one of the following holds. So these are two critical points of index, J and J, well, J plus 1 and J. Okay, I plus J less than or equal to N minus 2. I less than J. And a third case, which I won't write down, a Whitney trick conditions. Okay. Oh, I forgot to say here in the second case, we have to assume the Whitney trick type of conditions, I between 3 and N minus 3, or I equals 2, and V naught minus Y simply connected, or I equals N, I equals N minus 2, and pi 1 of V naught minus X simply connected. All right. So that you can do the Whitney trick. All right. So let me do the simplest case, which is the first one I talked about. The index at Cj is greater than the index at C naught, which is I, for all 1 less than or equal J less than or equal to. These critical points in W naught all have greater index. So we have our fixed disk, D naught, and we have all these ascending manifolds, A1 to AJ, AN, and they're all disjoint. So there exists a Riemannian metric on W0Q such that all these disks are gradient disks. So this is the descending manifold with respect to the gradient vector field. These are ascending manifolds with respect to the gradient vector field. That's easy to do because they're disjoint. So around each, you can take a little Morse neighborhood, disjoint Morse neighborhoods, use the standard metric in those neighborhoods and extend to get a metric on the whole manifold. Okay. And now, okay, so now D naught then is gradient below V naught. Okay. I mean, I guess it should be a Riemannian metric on all of W. No problem doing that. Okay. Now I have another disk, which I've already deformed so that D above V naught is equal to D naught above V naught. So the only thing that I worry about is what the disk looks like from V naught down. And I can describe the disk as a map of S I minus 1 cross I into W0Q, which is linear. It's an embedding, and it's linear in the I factor. In other words, if you take the function f looks like a linear map, an affine linear map from I to 0, 1. So the embedding E followed by F is projection onto the second factor, followed by an affine linear map from S cross I to 0, 1. Okay. And yeah, so this is a family of horizontal spheres that make up the descending disk. First thing you can say is, I'm going to look near one of the critical levels. I know this disk does not pass through any of the critical points. That's forced, for example, by this condition. But anyway, this is supposed to be a descending disk, so it can't hit any of the critical points. So if I look at the level that has a critical point in it, the intersecting sphere is disjoint from that critical point, and therefore there's a small vertical region around the critical point so that the sphere may move, of course, but nevertheless the full gradient flow on this whole region is disjoint from the critical point. So near each critical value, there exists a vertical cylinder, vertical with respect to the gradient flow, containing the intersection of this embedding, intersect the region, this is A to B, F inverse A, B. Just because everything is continuous and the sphere at this level, critical level alpha, is disjoint from the critical point. Okay. So the schematic picture I have now is, here's V naught, here are the critical points. I have this straight line disk, which is over here, gradient flow disk, and now I have another disk, but it's vertical in some small neighborhood, time neighborhood of each critical point. And then after that, who knows what it does. So here's the first critical level, and there's a little band about that critical level where the thing is actually a vertical gradient flow. Likewise here. Now I have these ascending manifolds. Well, I see, maybe I should draw the critical point on the other side so I can make this. Suppose the critical point were over here. Then I have this ascending manifold, which may meet the isotopy, but it doesn't meet it in these vertical regions. Okay, so now consider the isotopy I1, which goes from the top to the top of this first vertical region. So I1 is some map of the sphere across a subinterval into W0Q, which is a horizontal embedding. Each sphere cross point goes into a level. You can think of this as an isotopy, well, view it projected back to V0, view this as an isotopy in V0, from here to here. I want this to be a claim I can make by a small deformation. I can make I1 disjoint from the ascending manifolds A, or A intersect V0 if you think of it in V0. And that's because the codimension of the ascending manifolds is equal to the index of the critical points, and therefore is strictly greater than I. And this isotopy is a one parameter family of I-1 spheres. So by general position, I can make the isotopy miss the ascending manifolds. So I'll make this first isotopy. So here's the vertical one. First isotopy is actually disjoint now from the ascending manifolds. Well, I can simply push back to the vertical, and because the isotopy misses the ascending manifolds, pushing back to the vertical using the product structure also misses the ascending manifolds. That's what I do down to here, and then I just carry this vertical segment along. And so I end up with my path being vertical, a gradient path, at least up to the first, just past the first critical point. Then it continues to do this stuff. You just repeat the same argument again to change these, deform these isotopies slightly until they miss the ascending manifolds, and then use that to push back. And in this way, you get a deformation, missing all the ascending manifolds from the original path back to the vertical path, and hence pi naught. I've deformed D back to D naught, showing that pi naught vanishes. Let me just say a word about what happens in case 2 when the index at Cj is equal to the index at C naught, which is I. Here, this argument no longer works, this perturbation argument. In these isotopies, the ends are disjoint. So you have a map of Si-1 cross I into, let's say, V naught. The ends, Si-1 cross 0 and Si-1 cross 1, are disjoint from the intersection of A with V naught, which we're calling Y. But the codimension is now, codimension of Y in V naught is I. So this isotopy may well cross the ascending manifolds, may well cross I in a way that you can't get rid of. But in fact, what you can do is concentrate all those changes at the very top, this is V naught, and here's a slightly lower level V naught prime, you can actually push the isotopy so that this part of it is disjoint from the ascending manifolds. And then the funny business happens up here where in between V naught and V naught prime, there are no critical points, but you may cross the ascending manifolds up here. And then you continue to repeat the argument. You change the path up here, adding more intersections as you do more finger moves, but the rest of the path is vertical. So you end up with every descending disk is homotopic to one. That's some isotopy between V naught and V naught prime, and then vertical after that with respect to the gradient. And so then it's just a question of these intersections. It's just this isotopy and the way the isotopy meets the various components of Y up to deformation. And you have to have the Whitney trick to show the isotopies in V naught prime in that manifold are given up to deformation by the intersection numbers. With components of Y. The Whitney trick tells you if you have excess components, you can get rid of them. And so all that matters is the algebraic number of components. So that's the map, D minus D naught. D goes to D minus D naught in H1 of, well, V naught comma V naught minus Y, which is isomorphic to HI of W0 Q on VQ. So that's how you classify the descending disks when all the critical points have the same index. The argument in the third case is similar. It's slightly more complicated, but it uses the same ideas. And I won't go through a third case. Similar, again, you need, you use the Whitney trick in one of the cases. Okay, to show that they're pi naught, in that case, pi naught of D is trivial. All right, so let me just say what's going to come next. Now we're going to use this basic result. Well, we have to, I guess in my lecture on Wednesday, what I'll do is talk about the two critical phenomena we need to study, the local models for the birth and death, and then the local model for what's called the swallowtail. These are singularities. The swallowtail is codimension 2. The birth, of course, is codimension 1. I'll talk about elementary paths for birth. So I'll talk about the nature of the linking circle to a swallowtail. And then once we have this crossing result and some information about the bursts and the swallowtails, we're in a position to start simplifying the diagram. So that's what I'll do next week, is I'll take all of this stuff, these techniques that we're developing here, and start simplifying the diagram, putting the critical values in ascending order by index, then starting to get rid of all but two levels worth, and then I have to do the algebraic K-theory part of the argument to finish off the last two levels. Anyway, that's what I have in mind. Any questions? So I don't expect anyone to have been able to follow the details of the argument. I hope you've been able to get a flavor for what's involved in these arguments. All right, those of you who are hanging in there, I will see you. Hi, Granana. I'll see you on Wednesday, usual time. So long.